All right, we are going to continue our discussion of light by talking about thermal radiation, the electromagnetic spectrum, and black body radiation. When you send white light through a prism, like light from the sun or from just a regular light bulb, you get a rainbow, right? You get this continuous spectrum. But if you look at a light with maybe one type of gas in it through a spectroscope or a spectrometer, you would see discrete lines like we've talked about in the previous lectures. So why should this be? Why do we see a full spectrum from some sources and not from others? So in sources like a light bulb or the sun or even glowing metal, the electrons are unbound, right? There are no defined states, so the electron can be excited or de-excited to a range of energies. What you're seeing is basically a distribution of photons. If the electron is bound in an atom, it's constrained, right? They are only allowed specific energies. So a perfect emitter, what we call a black body emitter, gives a full spectrum with the peak wavelength corresponding to the temperature. Okay, so this illustration shows four different black body curves, four different emitters. And you can see the peak moves from kind of red to green to blue. Right here, we have just a peak in the visible light, and it kind of decays further out. Uh, the peak here is a little bit more in the red, still in the visible, but in the redder wavelengths, and its intensity is not as high. We go down a little further still, and the peaks are followed by these blue dots here. So where the peak is means that the light will have kind of a different tint, right? So right here, we maybe be able to see this light, but it will have more of like a redder tint. Up here, it will look probably a little greener, maybe a little bluer, yellower as well. And down here, these peaks are outside the visible spectrum at all. Um, the intensity, I also want to draw your attention to, it goes down kind of in accordance with the temperature, right? This tall peak here has a temperature of about 5,000 Kelvin, and we go down to 4 to 3 to 2,000 Kelvin. So when thinking about black body or thermal radiation, you can think about a piece of metal that you're heating up. So as we heat up the metal, the intensity goes up and the color of the peak changes. So a cold piece of metal, it won't glow at all, right? It'll just look like a piece of metal. But as the material starts to heat up, it will start out red, then white. Then when it's extremely hot, it would glow kind of a bluish color. So the distribution of these wavelengths goes according to this equation. So lambda max, this is the peak wavelength. It is basically 3 million divided by the temperature in Kelvin. And the units you get from this ultimately are nanometers. So hotter temperature corresponds with shorter wavelength, which means greater energy, and cooler temperatures correspond with a larger wavelength, which means lesser energy. So hotter temperature, shorter wavelength, cooler temperature, larger wavelength. And you can see how this kind of corresponds to when we're looking at actual stars, right? If we see a star with its peak emission in the blue or maybe even the ultraviolet, a little bit outside the visible spectrum, um, we know that this is basically a pretty hot star. I would call it a spectral type A. If we get something kind of in the middle, like a yellow star in the middle of the visible spectrum, this is a star very much like our sun, a yellow star. It's about 5,000 Kelvin on the surface. But then we also have much cooler stars that peak kind of in the infrared. And they're red stars, a lot cooler, a lot smaller, about 3,000 Kelvin. So just a little review of what we have learned so far. So energy of a mechanical wave is proportional to the square of the amplitude, but that's not true for light, for photons. Energy of photons is strictly proportional to the frequency. In atoms, electrons are bound and energy levels are quantized, and this leads to discrete lines in the spectra. Blackbody radiation involves unbound electrons that can have a range of energies. So these are things that are important to understand. And we can talk about these a little more formally with Kirchhoff's laws of radiation. So these describe the spectra emitted by solids, liquids, and gases of different densities. So a solid, liquid, or dense gas will radiate at all wavelengths and give off a continuous spectra. An excited, low-density gas, like what you might find in a neon tube, will emit light at specific wavelengths and produce an emission spectra. And another possibility is that light from a continuous spectra will pass through a cold, low-density gas. That low-density gas would absorb at discrete wavelengths, and you would get an absorption spectra. We saw examples of this in the last lecture. We have kind of been de facto talking about visible light, but the electromagnetic spectrum includes much more light than that. It goes from about over here, 10 to the negative 14th meters in wavelength, all the way up in the radio to 10 to the 4 meters in wavelength. Um, Different sources will also have different wavelengths or frequencies, which means that they have different compositions and temperatures. Also, the way we would detect this light may vary, the different wavelengths. And I want to note like the higher energy light than what we can see, we have gamma rays, X-rays, and UV. These are all higher energy lights than we have the visible spectrum, really a very narrow range. We see a very narrow range of light. Then we have lower energy infrared, and basically kind of radio wavelengths around here. And microwave in here as well. Um, it might seem like microwave might be out of place in the lower energy part of the spectrum because we use microwaves to heat up food. But this is where microwaves live, infrared microwaves and radio waves. So like I mentioned, we would use different methods to detect each of these wavelengths of light. And one of like the biggest problems that we have in astronomy is that Earth's atmosphere is only transparent to a limited um, range of wavelengths. Really just kind of the visible, a little bit of the UV and the radio. So this is what we call atmospheric opacity, basically how transparent is the atmosphere to different wavelengths of light. 100% means 100% blockage, like we are not observing in these wavelengths from the ground. And you can see here, like gamma rays, X-rays, and the UV, most of the UV, 100% blocked by our atmosphere. We have a little window right here for visible light. Then we're back to the infrared where it's pretty much always 100%, 100% blocked. Then we have a massive window for radio waves, so we can do radio astronomy easily from the ground, except for really long wavelengths. That is also blocked. Here it kind of shows what types of telescopes we need for each. So we need space telescopes for these high energy wavelengths of light. We can view from the ground for the visible, but once we get in the infrared, we are back in space, and then we can view radio waves from the ground. Most of the electromagnetic spectrum is invisible to us, right? Our eyes just aren't equipped to handle it. But I want to focus in on the UV for a second, the ultraviolet, and how it causes some objects to glow or fluoresce. So fluorescence is when UV light causes something to glow. Um, UV photons may excite electrons up several energy levels. Remember, UV light is pretty energetic, so it could excite electrons within an atom or molecule. The electrons will then decay, though, and they will emit photons corresponding to, the different energy levels. So this means that objects could re-emit photons in the visible range after being excited by UV light. And this usually happens in a green or a yellow color. And this is really consistent with the orbital picture of bound electrons. And right here, this is kind of an example of what might happen. You get blue or UV light exciting this electron up several energy levels, and then it kind of bounces down these energy levels and emits some green light when it finally goes back down to the ground state. Here is just a picture of this happens, naturally. These are just rocks that happen to fluoresce. They happen to kind of go through this process over here, and you can see they're glowing in kind of greens and oranges. A little bit of blue you can see. So it's kind of wild a little bit that we even know about invisible light. Like really when you think about it, right? How did we even figure this out? So this is attributed to William Herschel and his prism and thermometer experiment. So what Herschel did was he shined a white light on a prism and got the rainbow of color that we all expect. He put a thermometer right in each of these colors and he got a different reading at each color. Like each color was ever so slightly a different temperature. So Herschel had a thermometer in the shade, so he had, something to compare his other thermometers to, right? A control. But he also placed a thermometer just to the side of the red light, but outside of the spectrum. But this thermometer also showed a temperature above the quote unquote shade temperature. So he reasoned that there must be light there that we couldn't see. And this is really the first evidence we have for invisible light, which we call infrared, because it's kind of below the red. And you can see kind of here a little schematic of kind of what he did. So the sunlight shined through a prism, separated into all the colors. We had thermometers placed in each one of the colors, and then one outside, like below the red, like infrared. That's what that means. And he found actually an increase in temperature in this thermometer that was outside the spectrum. Okay, so that is all for this lesson. Remember, if you have any questions, just shoot me an email or come by office hours.